Good evening. It is 7 p.m., but no one has joined yet, so we'll wait for some more time. Good evening, Indranil and Prashant. I mean, could either of you confirm if I'm audible?
Yes, sir.
Okay,
You're
thank
audible,
you.
sir.
So I'll just share my screen. So, good evening and welcome to week 6 of the live sessions for Fundamentals of Additive Manufacturing Technologies. I am Sourav Goswami, a PhD candidate at IIT Bombay, and my field of work is also in the broad area of additive manufacturing. So, as usual, our agenda will include first the recapitulation of the contents that were covered in this week. So, mostly to do with the sheet additive manufacturing processes. And in the later half, we'll look at some problems from the course contents of this week. So this week, the course content is mostly theoretical, and I saw that the assignment itself covers a good lot of that theory. So it should be easy for you guys. Still, I hope this session will help you clear any pending doubts which you might have. And for seamless communication between us, I will request that you raise your hand and then I'll call out your name and then you may unmute and speak. Once we are done conversing, please turn off your microphone again. And otherwise, please remain muted at all times. Thank you. So for recapitulation purposes, we'll make use of Professor Kapil's slides. So in the first lecture this week, many sheet additive manufacturing processes were covered. Among them were the cubic technologies LOM, ERA's paper lamination technology, solid dimensions plastic sheet lamination, CAMLAM, which is a computer-aided manufacturing of laminated engineering materials, and NX Corporation's offset fibers. So not much used, but yeah, for the sake of completion, we'll cover all of them. And for sheet-based AM also, uh, Professor Kapil has displayed this classification based on the various subsystems that are used. So in a sheet-based AM process, the subsystems can be first the materials, second the approach, and for approach you have two primary ones. Either you form and then bond, or you bond and then form. What these things are, we'll discuss as we go along. Third is the cutting method, then the bonding method, and finally the joining of the regions. Just a second. I seem to be having some problem with my pencil. To be stuck at my end. Indranil, Prashad, could one of you please confirm?
Yes, sir. Audible, sir. You are.
No, no, audible, okay, but is the slideshow or the PDF, is it moving?
Yes, sir. Yes, sir. Okay. Fine,
Okay,
sir.
okay, thank you. Thank you. Yeah. Uh, so since in sheet-based AM, our raw feedstock is in the form of sheets. So, and you have a stack of them. So many on top of each other. There are two ways we can process them. Either so by slicing the STL file, we are already aware that what is the contour needed in each slice. So I know what I need for slice 1, slice 2, and or layer 1, layer 2, and layer 3. I can either previously cut out that shape, such as in this case, the star is cut out from this sheet. I can form these individual contours from each of the slices and then finally bond them together using any suitable means, such as thermally activated glue or some ultrasonic based processes or even plain adhesives. However, this will have certain caveats. So handling the cut pieces is very difficult. Why that is? Because A, it is not necessary that each slice will have only a single contour, only a single geometrical shape that is being cut out. So it might also be the case that for a particular contour, for a particular slice, you have these multiple discrete contours corresponding to the object that we are trying to print. And once they are already cut from the sheet material, it will be very difficult to handle them. We will also lose the sense of alignment where they're supposed to be placed. And in general, this may lead to errors in our final printed part. Again, these pieces may be odd shaped, and any loss of alignment will simply compound the errors as we go further. Then, in many of the sheet-based AM processes, the raw feedstock is of a very flexible nature, such as when we use paper. So, any sort of disturbance, say such as wind or any other ambient disturbance, can easily move it or bend it or it can easily be misaligned in the process of bonding. Again, the support mechanism will be needed, and the raw feedstock which is not very rigid would definitely require this support material. This support can easily be provided from the pre-existing stock, such as in the case of these bond and form processes, where the previously built layer can actually act as the support for this next incoming layer. However, once we have already separated the contours from a slice, there is no way to actually provide them the support. So simply they may bend over or they may lean over. For the bond and then form approach, first we simply bond all the based on the number of layers required and the build volume. We index the raw feedstock and then we bond those multiple layers together. Then from this final build volume, we, of course, during this bonding process, from each layer, we'll be simply scanning our contour, say for layer L0, L1, and so on. However, these will not be fully removed. They will still remain to continue to remain in the feedstock. They will, however, be scanned out, of course. Along with the contours, these grid lines will also be scanned. And primarily, we are scanning the area which is not needed for us in each layer. And later, these grid lines will be moved by the process called decubing. And if it is the case that there are two contours, so an inner and an outer contour, then this interior region may also have some grid lines cut. And whatever region I have highlighted in black here is the undesirable region. Those will be removed later. The non-highlighted parts are the desirable region. And we see that the previously built layer is actually acting as a support for the next incoming layer. So yeah, these advantages are summarized here. Handling is really easy. All you have to do is simply index the reel. By indexing, we move a well-defined fixed amount in each pass, and that takes care of the next layer that is coming in. The remaining stock acts as a support material, whereas in the previous case, there was a need for some external support material which was often not available. There is one drawback, which is the decubing process. So decubing actually refers to the removal of this. Let me magnify. Decubing refers to the removal of this grids that are to be cut out or eliminated later. And since you will have these grids in successive layers, what they'll do is, in the end, you will have end up having something like a cuboid in 3D space. So corresponding to each layer, and since you are bonding all of these layers first and then forming, you'll end up with a cuboid volume, which you will have to remove at the end. This process is very time consuming, as well as it requires ample skill and patience because your decubing process will actually determine the final surface finish of your finished part. Hence, it is very time consuming. And of course, it is suitable for flexible materials as well as rigid materials. Now, the first technology that we encounter is actually the laminated object manufacturing by cubic technologies. So LOM stands for laminated object manufacturing, which actually utilizes paper as the raw stock and uses a bond and then form approach. So we discussed in the previous slide why, especially for materials like paper, which are very flexible and which need the support structures, the bond and form approach is the only practical way to go. For cutting of those contours, it uses a laser, and bonding is used done by an adhesive, and the entire region is joined. Now going to the details. So it's an automated fabrication process in which a 3D object is constructed from solid CAD representation by sequentially laminating the part cross sections. And just like any other AM process, this also has three phases, which are pre-processing, build, and post-processing. In the pre-processing stage, as usual, we prepare the CAD file, convert it to STL. If you're opting for an indirect slicing, if you're opting for a direct slicing, we can also slice directly from the CAD file itself. The object is positioned and oriented in the desired place, and the presence of horizontal surfaces is especially detrimental to laminated or to any sheet additive manufacturing process, especially to LOM. That is because, as we were discussing, those horizontal surfaces will require the explicit support structures. And at the end of the process, when we remove all those grid lines by decubing process, the removed support structure might leave some remnants on the build surface if they are horizontal. And when they are horizontal, the contact area between the support structure and the build surface is the maximum. So two things can happen. Either some remnant of the support structure can be left on my part, or with the support structure, it might also be possible that some part of the build goes out during the decoupling process. In either case, the final part finish is hampered as well as the geometry is distorted. So it is often preferable to avoid or minimize. Of course, we cannot always avoid, but what we can do is we can minimize the number of horizontal surfaces in this process. And as usual, the next step would be slicing. And then we set the beam parameters, the process parameters such as beam diameter, offset, grid size for normal and fine cutting. So you can have some degree of adaptive meshing, I can call it, for the grid cutting process. However, for the slicing of each individual layer, I do not have a adaptive slicing available. So all slices will be of the same thickness. This is also one of the disadvantages of most uh, sheet-based additive manufacturing processes. Now, the build process is highlighted here. So on the right, we have the schematic as well. As discussed, we have the laser as the cutting source. This will perform all three cuts. So which are first the parting cut for indexing. So this, if I highlight it in black, this outer periphery is the parting cut, which actually defines the limit of my or the boundary of my build volume. The second would be the contours, so both interior and exterior contour. And third would be the grid lines. This is connected to an XY pointing device. And we see that for the case of LOM, we have two rolls of paper. First is the material supply roll, which supplies the material in each pass. Second, we have a take-up roll, which is taking up the remaining material after this parting cut is made. So we see that here, after the parting cut, this area remains hollow. Now, in each layer, the outline and the cross hatching is performed by this laser. This is our build block which is getting deposited. This final build volume will take either a cubical or more generally a cuboidal shape from which the decubing process will remove all the unnecessary regions. And with each pass, the platform moves by the designated height. Also, to actually bond each layer of paper to the previously deposited layer, a hot roller is used, which is actually a laminating tool, and it causes adhesion between the paper surfaces. So it is possible that a thermally activated glue is actually used between the paper in on the bottom side or on the back side of this paper roll. And when it is activated by the use of this hot roller, it causes the new layer to stick to the previously deposited layers. Here the three processes are again shown in brief. So when a new layer is added, first the bonding operation is performed by moving of this laminated roller, and then the cutting operations, which will include this parting cut over here for the boundary, and then the exterior and interior contours, and of course the grid lines as well. As we were discussing, the post-processing step is actually the most time-consuming and also perhaps a very deciding step for the case of these sheet additive manufacturing processes, especially long. So once all the layers are made, the build volume is a rectangular block, or I think it is better to say a cuboidal block. So this is parted off from the table using a very thin wire rope, and the unwanted material inside, in case you have some interior contours and surroundings, are removed using hand tools. This process is called decubing and may take several hours. So this is very concerning aspect because anyway, mostly these additive processes are often called slower compared to the conventional processes for some simple geometries. And if just the post-processing step of the support removal takes several hours, which is in addition to the build time, then it is really concerning. And the part after being finished, it can also be painted if needed and can also be given a lacquer coat to prevent it from absorbing further moisture. So here we see that even if like very complex and intricate geometry can be made using these laminated object manufacturing processes. However, the build volume which we actually end with at the end of the build process is cuboidal, and significant amount of post processing, which also takes a lot amount of time, is needed to actually extract that geometry. And as we have been discussing, this process has several advantages and disadvantages. One of them being that only the boundaries have to be addressed rather than scanning the entire region, such as say in the case of SLA, where you had this VAT which housed a build platform, and this entire part was in resin. Maybe you had some pre-deposited geometry here, and for the current layer, whatever region was available in my slice, this entire region had to be scanned, say either by raster or zigzag or any other means. But I had to scan the entire volume or the entire region. However, in the case of laminated object manufacturing, I need to only scan the boundaries because the feedstock material is already present. And there is no additional curing step as such, only some addition step. And thus, this process is very fast as the build volume is proportional to the surface area of the object, not the volumes. Again, a CO2 laser is suitable, whereas for processing some other metals, some other feedstocks such as say metal powders or metal wires, we may use or we may need lasers which are fiber laser or diode lasers, solid state lasers. Here, CO2 laser is sufficient and also suitable for cutting of materials like paper and even some ceramics. CO2 laser again is very cheap and even the control is very simple compared to some of the more advanced processes. And it is not hazardous really, it is also suitable for office environment. Thus, no special protective environment is needed as there is no scope of oxidation. In fact, some of the processes, as we'll see later, actually actively remove the oxide layer from the materials in order to enable the diffusion and joining. However, the proper exhaust is required. Also, we know that the CO2 laser cannot be operated without the exhaust. The feedstock, which in this case is paper, is quite cheap, and the parts are strong, almost wood-like. However, the primary disadvantage of LOM, and we can say that for most of the sheet additive manufacturing processes, is the lack of adaptive slicing or the fixed layer thickness. Thus, for regions which have a very simple geometry, we cannot actually make use. So, just like we have seen, say you have this arch-shaped geometry, which we have to say deposit. So here, ideally, we would have done is that we would have done some coarse slicing here and done maybe some comparatively finer slicing in these regions to capture all the geometrical intricacies. However, this is not possible in the case of sheet additive manufacturing as the layer thickness is fixed. Thus, we cannot actually make use of the adaptive slicing techniques. Again, grid cutting takes much more time than object cutting does. Post-processing time is far greater than the build time, which is undesirable. So that is related to the decubing. And also, the grid cutting time itself is far more time consuming because we, depending on the geometrical intricacy, even this may involve some finer grids in certain region. And here we may opt for some coarser grid. And we see that a far larger area has to be actually scanned for cutting out these grid lines rather than my contours which are of actual interest to me. The horizontal surfaces, as we discussed, pose problems. It is also prone to fire accidents because of the feedstock. Feedstock is paper. Even some other processes, such as powder-based additive manufacturing, are also susceptible, and especially powder can explode. So this is not a unique drawback. And for this specific technology, the product development has not been so active, as well as the marketing strategies are poor. Hence, it is almost obsolete. Okay, this is an example which highlights the actual ratio of the grid cutting time to the contour scanning time. We'll do this example in our problem solving session. This is an example part which has been built by this LOM. The next technology which we will look at today is the Kira's paper lamination technology, which uses again paper as a raw material, and approach is also bond and form. However, rather than using a laser, it only uses a simple knife as the cutting method. This reduces cost and complexity further. The bonding method is again adhesive and the entire region is joined. So most of the working principle would of course be similar to the laminated object manufacturing. And the primary difference being that we have a mechanical blade here which is cutting instead of a CO2 laser. In this case, the toner rather than thermally activated glue is used as the binding agent. And another primary difference is that in the earlier case we had a laminating roller or a hot roller, but here we have a hot plate. This hot plate makes the process faster because I am bonding the entire region at once. Also, it has several other advantages, such as it removes the bubbles and voids to a large extent. Also, it minimizes the internal strains. It results in more uniform application of pressure or uniform pressure, and even the layers do not slip, which would have been the case during rolling. So in rolling, the laminated roller moves from one end to the other, and this may lead to some slip or some shear between the two adjacent layers. However, here we simply have a downward motion of the hot plate, and thus there is no scope for any shear. The layers do not slip between each other. The build volumes may be smaller than cubic loom, but again they are more accurate. And here only, so I think it says only one roller is used instead of two in cubic loom, because in this case the indexing process is inherent to the Kira machine. There is no parting cut to be made, and there is no take up roller as well. So only the material supply roller is used. The pre-processing step would be the same, and the only additional thing is that some buffer layers need to be pasted on the machine build platform. This pasting, as we saw in the video that was shown in the lecture, is done by the very simple adhesive, uh, such as one example can be the Fevi stick that we have. So something like that, very similar. And you'll be, I think some of you might be aware that such adhesive is also used for FDM based processes where at first we apply some of that adhesive on the build platform at the start of build to ensure some good adhesion. And in the build process, the sheet alignment mechanism actually adjusts the printed sheet of paper onto the previous layer. The first layer actually starts from the table and we paste some buffer layers on top of it. And the hot press or the hot plate moves over them with the printed sheet at high pressure. The high temperature and pressure actually melts the toner, which is some sort of a resin powder, and this leads to adhesion between the sheets. The hot press also flattens the top surface and prevents the formation of air bubbles between the sheets, as we discussed. The computer measures the amount of movement and compensates for any deviation. And a mechanical cutter, which is in this case the knife, actually cuts the top layer of the block along the contour of the section, as well as parting lines, which are excess from which excess paper is removed later. So I might have misspoken. Apparently, there is a parting line, but we'll see that in some of the later processes, even this parting line is not needed. And we repeat all of these steps for each of the layers until the entire part is built. Post-processing would again involve decubing, which is similar to laminated object manufacturing. Here we have a schematic representation of Kira's paper lamination technology. We see that the cutter plotter consists of a mechanical knife and this heated plate and this single paper roll. So in this case, we have only one. This is the table. These might be some of the buffer layers, and these might be our pre-built or pre-deposited layers. Now, the heater is pressed on top of the paper to first bond the new sheet of paper to the pre-deposited layers, and then the cutting knife moves suitably in the XY plane to cut out the grid lines to make the parting cut, as well as to make the interior and the exterior contours. Once that is done, the next layer comes in, and again it is adhered by heating the resin between the sheets, and then the forming operation occurs. And finally, cuboidal build volume is extracted, and with the use of decubing operation, the support structure is eliminated at the end. This video actually illustrates the removal of the uh, cuboidal support structures or the decubing process. And we see that at the end of build, the build volume which we obtain is cuboidal. Some of the advantages of Kira's paper lamination technology compared to LOM are that the use of the flat plate, which is hot, and the high pressure to bond the layers. The model remains flat during this process. There is no shear such as would have been induced by the use of a laminated roller. And the block is again released after cooling, and thus all the stresses are relieved. There are no internal strains which might induce some residual stresses later. Of course, they cannot be zero, but they are at a minimum. And this implies that there is no curling or no distortion at the end of the build process because it is already relieved. A knife is used. This results in a smooth surface of the build module. And because of the absence of laser, which might lead to excess temperatures, and because of the lacing mechanism, there are no fire issues in this case, as well as not as hazardous as laser cutting. I mean, a mechanical knife is still hazardous, but compared to a laser, the hazard is less. And because of the very high lamination pressures which is applied by the hot plate, the products are 25% harder than equivalent wood, and they are very strong and strong enough for most prototyping processes. Rest of the advantages are similar to cubic slump. So these are some of the disadvantages. The slide says advantages, but yeah, these are some of the disadvantages. Among them, the fixed layer thickness, which prevents us from taking or utilizing the adaptive slicing techniques and saving some time. Again, grid cutting is far more time consuming than the actual contour cutting. Decubing again is the most time consuming part. So post processing takes far more time than the actual build process. Horizontal surfaces also pose problems as this is similar to long, and also it retains some of the other disadvantages of long. The next process that we encountered in this week is solid emulsions, plastic sheet lamination. So the previous two technologies, LOM and Kira's technology, actually used paper as the raw material. This one uses plastic sheets. However, similar to paper, because of the very high flexibility, the approach still remains bond and then form. A knife is sufficient for cutting in this case, and an adhesive combined with a masking agent, which we'll see later, is used as the bonding method. And joining occurs only along very selective region rather than bonding the entire region as we were seeing in the previous cases. So the raw feedstock in this case is the thermoplastic, which is often transparent, and adhesive in combination with a selectively applied release agent called the masking agent is used for binding the sheets. So in areas where the masking agent will be applied, the sheets will not stick together. And in other areas where the adhesive will be applied, the sheets will be sticking. So later, the masking agent applied areas can be removed more easily. And Professor Kapil gave a very simple analogy and very interesting analogy, such as when we have two strips of sellotape, which are self-adhesive tapes, and if we were to put a drop of liquid, such as water, on them and stick them together, the area which contains water will actually not stick, whereas the rest of the tape will stick under the action of the adhesive. So water in this case may be considered as the masking agent. And in this case, rather than the decubing method, which we encountered in LOM and Kira's technology, a method called peel away is used. And what happens is, very strategically, the support structures of the undesirable regions in each layer are very selectively adhered to the undesirable region of the next layer in some very small regions, such as to form a continuous chain across the layers. So say if I have a few layers here and this is say my undesirable region, which eventually I do not want. So between each of these layers, so it will be joined very selectively, say here to the next layer, and this will be joined here to the next, and so on, so as to form a continuous chain. And what happens is when my final build is finished, I can simply start peeling away or tearing off the undesirable region from the top surface. And because of the continuous chain, I can easily remove the undesirable region throughout all the layers. So here again, the pre-processing would include the preparation of STL file slicing, generating the toolpath, the gluing and the releasing agents, and again, in this case, we have to paste a few buffer layers. The build cycle would start with masking. So first we mark out the regions which we do not want to be stuck together. For the remaining regions, we apply the glue, then the ironing process. So in this case, yeah, ironing is used to actually bond the sheets together. Then they're cut using the mechanical knife, and some trimming operation is also performed as an afterthought. The post-processing includes peeling away of the support. So this is far faster and less time consuming than the conventional decubing process. The video also explains it very well. Now, the next process which we encountered was actually CAMLEM's CL. So CAMLEM simply stands for computer aided manufacturing of, okay, I will write it. So computer aided manufacturing of laminated engineering materials. So when you say engineering materials, it is mostly metals, alloys, ceramics, and polymers. There might be few others also, but these are the most the principal ones. And for Camlins CL. CL is simply the abbreviation from this Camlin CNL. So the material is, or the feedstock is ceramic. It uses a form and then bond approach. So I extract the useful region of the contours from each layer. I set them aside, then later align them together on top of each other, and then bond them together. So maybe I extracted this from the first, from the second, and from the third layer. I'll keep them aside, and through proper alignment, at a later time, I will assemble them together. The cutting method is again laser, and since we are cutting ceramics, I think CO2 laser is again the most suitable one. Of course, the power requirement may be higher than when cutting paper. The bonding method is through sintering because we know that ceramics can be actually bonded through sintering aided diffusion. So any conventional adhesive may not provide a strong enough bond. And again, the entire region of the sheet is joined in this case. It uses the principle of form and then bond. And as you see on the right here, the entire manufacturing process is outlined. So the solid CAD model is first prepared, just like in any other EM process, and the contour representation, which may be obtained after slicing of the STL file. Now the slice cutting happens for all the layers individually in the beginning, and it uses a laser. For ceramic, it can be a CO2 laser of suitable power. Then all the cut or the formed layers are stacked on top of each other. Now in this case, you have this hollow geometry in each contour, corresponding to which maybe you can place some cylinders and use them for aligning. But if this is not the case, then aligning becomes a real challenge, and which will also determine the final finish of your part. Finally, once all these layers are aligned together, they may be laminated or adhered together, or the layers may diffuse with each other through the sintering process. Once laminated, the conventional sintering and binder removal occurs, and then you end up with a finished component. Of course, during the sintering process, some volume of the built part will shrink. So this shrinkage has to be accounted for at the pre-processing stage itself. Now, a variety of materials can be processed via CAMLAB. Ceramic is given as one example, but it is also suitable for metals. So pretty versatile. And up to 5 materials can be used in the single machine. So it also has the multi-material capability. So maybe it can also be developed further for the manufacturing of FGMs or functionally graded materials. And for one of the commercially available machines, the specifications have been provided to us. So CL100 has a build volume of 150 cross 150 cross 150, and layer size can vary between 100 to 600 micrometers. Also, another interesting thing about the CAMLAM CL is that variable materials as well as variable layer thickness is possible. So it makes use of both multi-material AM and the adaptive slicing as well. So more versatile than all the sheet lamination or the sheet additive manufacturing processes we encountered thus far. The making of internal channels is possible, as we also saw in the example here. This cylindrical uh, cavity can be considered to be some sort of internal channel, which also helps in the alignment process. The precise depth of cutting is not required as it is form and bond approach. So in the previous cases where I already had a stack of pre-deposited material and I was adding another layer to it on top of which I was scanning my contour, I had to make sure that in the case of laser, the depth of penetration was short, as well as in the case of knife, I'm only cutting to a very shallow depth or the necessary depth. Else, I might end up harming or cutting on top of the pre-deposited layer also. However, in this case, case, since we're only cutting one sheet at a time, we need not be concerned so much. And the cutting depth may have significant tolerance. It need not be as precise. As well as here, no additional adhesive is required. The binder and sintering process is sufficient. However, because of sintering, some shrinkage will be introduced, which have to be accounted for in the pre-processing stage itself. The alignment becomes a big challenge because once the parts are separated, we may lose our reference points, and realigning the parts later can become difficult. And again, because of the form and then bond methodology, there is a lack of support structures. The last one for this lecture was NX Corporation's offset fibers. So this is really not a very widely used technique. It uses paper as the raw material and uses a form and then bond approach. The cutting is performed via a knife, and bonding is attained via the use of adhesive, as well as the entire region is scanned for joining. It is also similar to Kira Corporation's paper laminating technology. However, Kira uses the bond and then form approach. Here the approach is inverted. Here the form and then bond approach is preferred. And again, it also uses a mechanical knife, just like Kira's paper laminating technology. And the cut sheet of material is then transferred onto the laminated previous layer. The process and cutting and laminating of the materials is repeated until the whole part is obtained. So here we have something called a carrier. This carrier is akin to a plate on which we place our fabrication material, which is in the form of sheets. On top of the carrier with the sheet, we perform the cutting operation of the contours for each slice. And then by inverting the carrier, we place this new slide onto the pre-deposited build part. Once the new slice is added to it, and using the adhesive, the slice is adhered, the carrier weighted material or the unnecessary material is removed along with the carrier. So any thin fabrication material which can be cut and bonded to itself by means of adhesive can be used on the carrier. And the knife is used to cut the outlines of the cross sections. Of course, the depth should be such that it does not cut through the very carrier itself because it has to be reused for each pass. The parting lines are also cut as well as outlines for the support structures. And the film is then weeded to remove some of the negative material. So all these undesirable material regions in this case are removed, and the process is called weeding. The film is inverted as we discussed so that the carrier is facing up, and the new layer is brought in contact with the growing object. The carrier is then peeled off to reveal the new layer which is just added. However, as we can already foretell, the precise alignment of this carrier on top of the pre-built object will actually decide the geometrical accuracy and tolerance of my finally built part. As long as we can assure or control that alignment, things might turn out okay, but it's very difficult. Again, just like CAMLM CL, a wide variety of materials may be used, and there is minimal shrinkage as there is no sintering step. Other advantages are similar to Kira's laminated object manufacturing or paper lamination technology. The cutting forces, however, have to be very precise to avoid cutting through the carrier plate. The alignment needs to be very precise because we are going with a form and then bond approach, and a lot of material is wasted. Now we'll quickly do a recap of the second lecture that was covered this week. So again, it covered some more sheet additive manufacturing processes. Among them, the most important being ultrasonic consolidation. So ultrasonic consolidation actually uses the metal sheets as the raw material or feedstock and uses a bond and then form approach. The unnecessary parts are removed by a milling operation. So one thing we will all appreciate is that as far as sheet additive manufacturing processes are concerned, they are inherently hybrid in nature because there is an adhesive step where by the use of some bonding techniques such as by the use of adhesive or by sintering, the layers are stuck to each other and thus the part grows. However, the unwanted material is removed from each layer through some subtractive technology, such as milling in this case. So it may be said that all sheet additive manufacturing processes are inherently hybrid in nature. That is, they consist of both the additive and the subtractive steps. The joining region in this case is also selective, and the bonding method is through diffusion. Now, ultrasonic consolidation is a hybrid process, as we already discussed. And it actually uses the principle of the ultrasonic metal welding with in situ material removal process through a 3-axis CNC contour milling. And because of the moderate pressures and the low temperatures, it is a solid state process. So the temperatures that are encountered are typically say 30 to 50% of the melting temperature. So we remain in the solid state regime only. There is no melting involved. It uses the principle of bond and then form, and it was first patented by Solidika Inclusive in 1999. Solidika Incorporated in 1999. How we apply the ultrasonic energy to this process is that a power supply first converts the mains electric alternating frequency, which is typically like 50 hertz or 60 hertz, 50 hertz here, to an ultrasonic value, which is around 20 kilohertz. And then this electrical energy or this electrical energy is converted to mechanical energy through the use of a transducer. A transducer, as you know, is a device that converts electrical to mechanical energy. And the actuator then mechanically drives a booster, which further boosts the amplitude of these mechanical oscillations. And finally, that boosted amplitude is supplied to a sonotrode. The sonotrode actually passes on these ultrasonic vibrations to the metal foil material which is underneath it, as well as it also provides some normal force. The welding force here is acting normally to the foil which is being welded. So it applies both a welding force in the normal direction as well as it applies those ultrasonic oscillations to the metal foil which is being welded. Here we have a schematic. So the welding speed in this case is actually the speed of rotation of this wheel, which will determine how fast we are going along the weld direction and diffusing or bonding the metal foil on top of the pre-deposited part. The transducer converts the input electrical energy into those mechanical oscillations. The amplitude of the oscillations are further amplified by the use of booster, and finally, they are passed on to the metal foil using a sonotrode. We use an anvil as the base of the machine, and on top of the anvil is a base plate. Often the base plate is of sacrificial nature, so it will be consumed during the build. And we see the previously bonded foils as well as the new incoming foil layer. And some typical dimensions which are used in this case is a thin metal foil of 100 or 150 micrometer thickness and 25 mm width. Is placed on a sacrificial base plate. Yeah, so as you were discussing, the base plate is often of a sacrificial kind and is consumed along with the build, is bolted into an anvil. The foil is compressed under moderate pressure and vibration of 20 kilohertz. The amplitude values in this case may range between 5 and 40 micrometers. And the sonotrode is provided with a rough surface, usually by some process like knurling. And this actually helps to prevent any relative motion between the sonotrode and the top of the incoming metal foil. Thus, the reference surface allows the sonotrode to grip the top surface and making it vibrate without any slip. However, this results in a relative motion between the foil and the base plate or the foil and the pre-deposited layers. This process is performed at room temperature only. There may be some temperature applied to the build plate, but other conditions remain ambient. And some heat is produced through the scrubbing of the mating surfaces and the bonding interface. However, still, the temperature rise is still limited to between 30 and 50% of the melting point. Thus, it is a solid state process. And the heated base plate uses a temperature of approximately 200 degrees Celsius to further accentuate the process. And as we discussed, there is a milling cutter which actually removes the unwanted region from each layer. Now, in terms of the working principle, ultrasonic consolidation is lying somewhere in between solid state diffusion bonding and linear friction welding. And how that is? Because in solid state diffusion bonding, there is no scrubbing of the surfaces. So there is no relative motion between the two surfaces. We just have very high temperatures, so typically somewhere between 50 and 90% of the melting point, as well as very high normal loads or normal pressures. So these loads will produce very high pressures to flatten the bonding surfaces, to fragment the impurities, and to produce atom to atom contact. So as we are well aware, no surfaces are or no two surfaces are absolutely flat. Whenever you have surfaces, they will have these peaks and valleys called asperities. And when you bring them in contact, the apparent area of contact is far, far larger than the actual area of contact. So only a fraction of the area which is apparently in contact is actually in real contact because of the nature of the morphological nature of the surfaces and the presence of these asperities. So by using the high temperatures, which is between 50 and 90% of the melting point, as well as the very high pressures applied through normal loads, these surfaces are brought in close contact, such as the real area of contact approaches the apparent area or the geometric area of contact. Of course, it will never be equal because no surfaces are exactly flat, but we'll try to approach the geometric area of contact. And by producing atom to atom contact, the diffusion is achieved. And of course, when surfaces are pressed together at high temperature, so you have both temperature and pressure acting, the atoms will diffuse along grain boundaries and close the voids in the contacting surfaces. The atoms will further condense and reduce the size of any other voids which were remaining. And based on the type of material you're using or the process parameters, this pressure application time can range from between a few minutes to a few hours. This is how the process was similar to the solid state diffusion bonding. Now, let us look at how it is similar to the linear friction welding. So, in friction welding, usually the bonding is solely dependent on the pressure and the frictional scrubbing. So, in this case, there is relative motion between the mating surfaces. The process begins with two pieces that are statically clamped, and If we have inertia welding, this might involve a rotation or relative rotation between the two mating parts. If it is linear welding, yeah, so in inertia welding, the parts are rotated, and in linear welding, the parts undergo some linear reciprocal motion. And the amplitude of this reciprocal motion can be pretty large, far, far larger than the ones we have in this ultrasonic consolidation process. The pieces are brought together under light pressure. So, as opposed to the solid state diffusion process where the loads were very high, leading to very high pressures. Here, the loads are very light, and thus the pressure at the interface is also light, which causes frictional heating because of the relative motion or scrubbing of the surfaces. Finally, a forging pressure is applied and the relative movement is stopped to form the final joint. The stress on the material due to scrubbing and forging causes the material to reach the plastic state, and the plasticity of the surface helps remove the surface impurities. And once the plastic state has been reached, permanent deformation can be had, and the two surfaces are forged together. So, ultrasonic consolidation shares many of these aspects. It is performed at an elevated temperature and the interfacial motion of the friction welding. So, ultrasonic waves travel through the bonding material, and what this does is actually lowers the modulus and the stress needed to reach a plastic state. So, we saw how in linear friction welding, it is only once the plastic state is reached that the two surfaces can be joined together. And here, the additional use of the ultrasonic waves lowers the elastic modulus of the material as well as lowers the threshold stress which is needed to reach the plastic state. So this is called Blaha effect. And the use of ultrasound in diffusion welding in an inert gas atmosphere or even a vacuum reduces further the time needed for bonding. So usually this process is carried out in under ambient conditions, but experiments show that if we are to further refine the conditions by using an inert gas or even vacuum, the process can be even faster. And the mechanism of bond formation has been widely studied, but still the exact principle or the exact mechanism is not very well known. Thus, it is rife for exploration, and aspiring researchers can very well work in it. Thus, the major phenomena associated are the mechanical interlocking of the surfaces, the melting of the interface material because of the high energies involved, diffusion bonding, and then atomic force across the nascent metal. So this is the surface that I was talking about, and we can see the asperities here. And we see that how the surfaces are never perfectly flat. They always have these asperities on them, and thus the actual area of contact is only a very small fraction of the geometric area. So one would assume that this entire area and also in the other dimension, this entire geometric area is in contact. However, actually only a very small fraction where these asperities are touching. So if I draw them or denote them by these small dots, these are the only regions where the surfaces are actually touching, which is at the asperities. So the actual area or the real area of contact is far, far less than the geometric area. However, by the use of this ultrasonication process, the friction and the ultrasonic waves may actually help to break up the oxide which is present on the surface. So we know that the surface of metal up to several microns or several micrometers of thickness consists of several layers such as the oxide layer, the BLB layer, some thermally deformed layer before we reach the nascent metal. And this process actually has the potential to break up those oxides and allow for atomic diffusion between the nascent metal layers. So when two relatively flat surfaces are brought together, only the peaks or the asperities, yeah, the surface asperities actually touch. Thus, the physical contact area is less than the geometrical area of contact. With ultrasonic consolidation, we actually make this actual or real area of contact to approach the geometric area. And ultrasonic motion causes the oxides to break up through a process called acoustic softening. which allows a direct contact between the pure metals, resulting in metallic bonding through atomic diffusion. The bonds are in turn plastically deformed by the shear vibrations, resulting in heat, which promotes diffusion and crystallization of the material between layers. Thus, the bonding is a true metallurgical bond. Further, the process is also aided by the transfer of ultrasonic energy into the metal, which effectively acts similar to localized heating and reduces the both the elastic modulus as well as the threshold critical stress needed to achieve or reach the plasticity zone. The ultrasonic energy shifts the curve. So this is some characteristic curve which shows the stress needed to reach the plasticity zone by reducing both the amount of heat as well as the stress needed to reach the plastic stress state. This was first observed by Blaha sometime in the 1950s, maybe 1955, and this is named the Blaha effect or acoustic softening. So here we see the schematic of the ultrasonic consolidation process. The surface is knurled to actually provide a texture and prevent any relative motion between the sonotrode and this top layer. Also, a normal load or pressure is applied. The excitation frequency is typically 20 kilohertz. Amplitude can be 5 to 40 micrometer. And because of both the frictional heating as well as the heated build plate or external heat, the joining occurs. The stiffness of the build piece is an important factor which determines how much load can we can apply as well as what is the amplitude of transverse vibration that can be applied. So the other process parameters which actually control the final build quality are the travel speed, which will actually help to determine the energy exposed per unit length of the welded track, the amplitude vibration, and this is directly related because higher the vibration amplitude, greater the ultrasonic energy delivered. However, does this mean that we can go on increasing the amplitude arbitrarily? Maybe not. So, a sufficient amount of ultrasonic energy is needed to actually induce that plastic deformation and fill the voids that are present in the sheets. If too much energy is input by increasing the amplitude vibration too much, the amplitude of vibration by too much, then the excess plastic deformation may actually damage the previously found bonds at the interface. So some cracking, or if the temperatures go too high, then even some melting may occur, which is undesirable. Also, the normal load is a critical process parameter, which flattens the asperities and determines the value of the stresses which will occur at the interface. Now, a sufficient amount of normal load, again, sufficient, so not too high, ensures good metallurgical bonding. If the normal load exceeds the critical level, the excess plastic deformation may again damage the previously found bonds. The base plate temperature is another such parameter, and suitable external heat can actually reduce the apparent stress required for the reaching the plastic zone. It may also help to enhance the atomic diffusion by providing them with some additional energy and can reduce the strain hardening behavior. The sonotrode texture is a vital parameter because if the texture is too deep, it will also reflect on the top plate and that may lead to the presence of some voids which cannot be filled. Thus, the texture cannot be very deep. At the same time, the texture has to be suitable so that it limits any form of relative motion between the sonotrode and the top layer, and it directly affects the amount of damage to the surface. The power draw is a measurable quantity which can be used to assess the different conditions of stick and slip at the interface. And as we discussed, the stiffness of the machine actually limits the amount of force which we can actually transmit to the bonding interface. The surface topography or the surface finish of the metal foil is another one. If it is not clean or if there are some contaminants present, even though the oxides can be removed by the ultrasonic energy, some contaminants may remain entrapped and they will influence the frictional characteristics as well as the final build. They may lead to some interlayer defects or even interlayer lack of fusion. Yeah, the presence of surface contaminants and oxides may prevent metal to metal contact and must be displaced. The geometric and uh, modular stiffness of the substrate are also direct influences of the resistive force produced by friction at the bonding interface. And the hardness of the materials is, of course, important. So, one very critical area where ultrasonic consolidation is used is actually in embedding these electronic fibers or maybe even electronic sensors into these metal strips. So, here we see that between the metal strips, we have these few fibers which can be imbued, leading to some smart materials or sensor embedded materials. And some researchers have already incorporated channels for fibers using some laser beam melting. So an additional melting step has been added to this ultrasonic consolidation process. It is suitable for bonding a large variety of materials. Here we already see a multi-material example where copper and aluminum have been bonded together. So these bronze lines actually uh, correspond to copper. These silver lines correspond to aluminum. And on the right, we have the compatibility chart, where we see that aluminum is compatible with most of the major engineering alloys we have used. Similarly for iron, and a very large array of metals can be mixed together and used. So multi-material additive manufacturing can also be performed. Now the process modeling step would actually involve modeling of all the forces that are present. And because of the normal stresses, we know that the contact between this sonotode, so this region right here, this contact will not be a point. In 2D space as we're looking at it, or in we can say that not a line. So this is not really a line contact. You would expect that if I have this cylinder on top of say this flat plate, so the contact will only be along a line where the cylinder is coming in contact with the surface. However, because of we know that because of the additional of the action of the normal forces, some Hertzian contact stresses will develop at the surface, and this contact will actually be not a line but an area contact. So if we isolate this region, which is the build plate, one foil of metal, and look at the forces acting between them. A normal force, which is P, acts on the foil. There is a sonotode friction force acting along both directions, depending on the direction of oscillation. And there is an interface force acting because of the friction between the foil and the build plate. Similarly, for the build plate itself, there is the normal pressure or the normal force acting from the anvil. There is this anvil force and there is this interface force. And since this is an oscillation, we can model it by some simple harmonic function. And if d naught is the amplitude, the displacement for this motion can be modeled as dt equals d naught sine 2 pi ft, f being the frequency of oscillation, and then the velocity and acceleration can be easily obtained. Then, using Newton's laws, the equation of motion of the top surface can be developed. The mass of strip in this case can very easily be calculated from the critical length or the length of contact that we just discussed multiplied by the width of the strip and the thickness of the strip. This gives us the volume which is in contact with the sonotode. And once we multiply that volume with the density, we obtain the mass. The contact length can be found from the contact mechanics equations as given here. And here, nu is actually the Poisson ratio, and E is the Young's modulus or the elastic modulus. K is Kolosov's constant and is computed in terms of the Poisson ratio. Thus, the interface force or the interfacial shear force can be calculated. And once the interfacial shear force is known, we can also find the total energy input. So here the energy input is nothing but the interfacial force times the velocity in the vibrating direction. And so this is force times velocity is actually power. And this power integrated over time will give me the energy. Again, the total energy supplied to every single point can also be computed. This can be had by calculating the dwell time. So if in this critical region, we look at one point on this top surface and how long it has been exposed to this force, so it will continue to be under the action of this force as long as it is within the critical length. And during this time, it may be subjected to several passes or several of the oscillatory motions. So the dwelling time can be calculated simply by dividing the contact length by Vt or the transverse velocity, the travel velocity, and the motion cycles, number of motion cycles can then be calculated by dividing this dwell time to the time period of oscillation. And then the total energy supplied to each point can be computed as the energy supplied in each cycle, which is E naught, times the number of cycles which the point has been subjected to. Advantages, of course, are multi-material additive manufacturing, the embedding of fibers, such as temperature and pressure sensitive objects, and no atmospheric control needed. It can be operated under ambient conditions. No typical safety hazards as such. There is no liquid to solid transformation as it is a solid state process. Thus, there are no residual part stresses. Very high deposition rates, and it can also be used for bonding metallurgically incompatible materials without the formation of any intermetallics or any deleterious second phases as such. It is also highly energy efficient and consumes as little as 5% of the energy required for conventional welding. The last process that we looked at this week included laminating manufacturing by the use of fasteners. So something like a tool and die process. This top is punch and die. So this top part is called the punch. The bottom may be referred to as die. And again, by using a form and then bond approach, where we remove the area of interest from each region, but in this case, preserve both the indexed sheet as well as my region of interest, I can form these two, which are a punch and a die. And then this punch and die can be actually used to manufacture objects through punching or even through some drawing like processes. So that brings us to the end of the recap. We'll take a short break. Then we'll look at some of the questions. The questions this week are mostly theoretical, but I hope they will help you with your assignments. So let us resume at 8:32 or 33. Thank you. Okay, so let us resume. So by just this short recap of the contents covered in this week, you should be able to answer most of the assignment questions as they were based on direct theory that was covered. We'll also cover some of the more interesting questions. So the first one asks us, which of the following materials cannot be processed by sheet additive manufacturing processes? And among the options, we have some aluminum grades, two of them, copper. So usually in any other additive manufacturing process, such as in DED, because of the very high reflectivity of these aluminum and copper materials, as well as the very high thermal conductivity, what happens is that the materials are not properly melted because a large part of the energy which is incident actually gets reflected back. So we have to, till now it's not, I mean, people have done it, but it's still not, cannot be performed reliably. And the additive manufacturing of aluminum and copper remains still an open challenge. However, in sheet additive manufacturing process, since there is no such, I mean, incidence of energy by use of laser beam, and we have already seen that there are many technologies such as ultrasonic consolidation or even CAMLEM, which can actually combine these multiple materials. In fact, for the case of ultrasonic consolidation, we already saw that material compatibility chart, which clearly shows that all of these materials can be processed. Thus, the correct option is that all of the above materials can be processed using sheet additive manufacturing processes. The second question is asking that the amount of ultrasonic energy that is delivered is directly proportional to the amplitude of ultrasonic vibration. Thus, can we use an arbitrarily high value of amplitude for ultrasonic consolidation? So this is an assertion and reasoning type of question that we have to make a choice as well as we have to provide the correct assertion as to why this choice is suitable. So it said that ultrasonic energy delivered is directly proportional to the vibration amplitude. This fact is given to us. So can we use an arbitrarily high amplitude? So maybe we can because the speed of travel scales linearly with the vibration amplitude. So even if we increase the amplitude vibration to say two times of original. So initially say I had a vibration amplitude vibration of D naught and later I make it D1 where D1 is actually twice D naught. To maintain the same frequency, all I have to do is simply increase the travel speed. So V naught will simply be equal to twice V1 and I perform some calculations using the typical values of frequency such as 20 kilohertz and the typical uh, amplitude vibration which is say anywhere between 5 and 40 microns. The speeds for travel would just be some 3 meter per second or 2 meter per second, which can be easily attained. So, while the speed of travel scales linearly with vibration amplitude and can be achieved easily, is that sufficient? Now, no, because the process would approach linear building. But this is not a problem as already the ultrasonic consolidation process borrows some of the concepts from the linear friction welding. So this is clearly out. No, because it can lead to cracking. And why that would be because it would actually damage the metallic bonds which have formed between the two surfaces. Now these forms bonds are deformed and because of the shearing of these bonds the excess energy is released which leads to metallurgical diffusion. But if we provide an excess amount of energy, it can lead to cracking. And also if the energy input is very high, it may also lead to melting of the feedstock, which is undesirable as this is a solid state diffusion process. So both options C and D are suitable, and thus arbitrarily high value of amplitude cannot be given even if it is possible to achieve such values. The third question asks us which of the following regions are subjected to relative motion in the context of an ultrasonic consolidation process. Now, as we are well aware, so there will several. So there is the contact between the sonotrode and the top sheet. Okay, so I drew it in the wrong direction. Sorry. So you would have the sonotrode in contact with the incoming foil. Would have the pre-built layer on top, which is itself consisting of several foils, and this would be on top of some sacrificial build plate, which is mounted on top of the anvil. So you have several interfaces here, and we are asked to find which of these regions are actually subjected to some relative motion. So the sonotrode sheet interface in the welding direction. So the welding direction would be this one, corresponding to this motion of the sonotrode. So definitely the sonotrode is moving forward, and that is why more and more material is getting welded on top. So definitely here we do have relative motion. The sheet interface between the new layer and the previously bonded layer. So while there is some definitely there is some relative motion because of this relative motion and the ultrasonic energy, the oxides layer are broken. So even this is probable. Interface between two previously bonded sheets. So the any such interface, such as this one or this one between two previously bonded sheets. Now this is already formed. So clearly there will not be any further relative motion between these. So this option is out. And the sonotrode sheet interface in the transverse direction or the amplitude direction. So we know that there are two forms of motion between the sonotrode and the top sheet. One is the welding motion, where the sonotrode is traversing over the metal foil. The second is this transverse motion, which is actually the ultrasonic amplitude. And we read how because of the knurling and the surface finish of the sonotrode, which ensures there is no slipping and relative motion between the sonotrode and the top surface of the top foil, there is no relative motion there as well. Thus, options A and B are suitable. Question 4 is asking us what is the Blaha effect. So there was a mention of the Blaha effect in one of the slides, and let us try to find out what exactly it is. So we'll go from the bottom to top. So the flow stress remains unchanged when an oscillatory stress is superimposed to a deforming specimen. But if this were the case, then the application of any additional ultrasonic energy would be of no use. And we already know that in processes such as ultrasonic consolidation, this application or the superimposition of this ultrasonic vibration actually leads to acoustic softening. So definitely the stresses will change. They will definitely not remain unchanged. But whether they increase or decrease, let us find out. So the flow stress decreases when a constant stress is superimposed to a deforming specimen. This might be true, but this is not the Blaha effect because we read Blaha effect in the context of ultrasonic consolidation. So definitely, rather than constant, the stress has to have some amplitude and it should be variable. And the flow stress increases when an oscillatory stress is superimposed to a deforming specimen. But this will not really be conducive because if I'm increasing the flow stress or the critical stress threshold, which is needed to reach the plasticity zone, by further providing it more ultrasonic energy, I'm simply making it more and more difficult to deform. And without reaching the plastic deformation zone, I cannot really have fusion between my metallic layers. So this is wrong. And of course, the flow stress decreases when an oscillatory stress is superimposed to a deforming specimen. This is the correct option, and this is actually the principle which is utilized in ultrasonic consolidation, first reported by Blaha and his partner. I forget the name of the other author in a paper in 1955 called the Blaha effect or acoustic softening. So another name for this effect would be acoustic softening. Question 5 asks us which step determines the productivity rate in cubic technologies laminated object manufacturing. So if we remember, there were several steps involved in the laminated object manufacturing process. These were the pre-processing, build and post-processing steps. And among the build steps, there were several such as grid cutting, the contour cutting, the time taken to index the paper onto the next pass, as well as the decubing operation, which was post-processing. So the grid cutting takes a significant amount of time. That is true. And okay, so let us write these types. TA, let the time taken for outer contour cutting be TB. For the indexing, let it be TC. And for decubing, let this be time TD. And let us try to arrange these in an increasing or decreasing order. So we can typically say that the sheet indexing time can be the minimum, followed by the contour cutting because it can have some intricacies. So it will be definitely more than the sheet indexing time. And because the grid is involves several passes as well as there can be some adaptive meshing. So in some intricate regions the grid has to be fine, and in other regions it can be coarse. So maybe the grid cutting time. Sorry, I'm yeah, using the wrong sign. Oh no, sorry. Okay. So even grid cutting time is larger than the contour cutting time. And finally, as we have discussed so often, the decubing time is actually the one which is the most lengthy and time consuming, as well as the most critical in terms of the final part quality or surface finish. And thus, it is actually the decubing operation which will actually determine the productivity rate. So might also say that this decubing time is far, far larger than the other time scales involved. So it will be option D. We have a numerical type question here, and we are asked to find the ratio of time taken for grid cutting to the time taken for scanning the outer contour for the given geometry. So as we are aware, in sheet additive manufacturing processes such as LOM, there are two steps, actually three. So there will be a parting cut to isolate the current canvas or the current region of the sheet which has to be bonded. Second would be the contour cutting, which includes both the exterior and interior contours. And the third would be actually cutting the grid lines. And to actually get an idea of the scales of these various processes, we have been asked to find the ratio of the contour cutting time and the grid cutting time for a given example. So let us go ahead. Let us try to find the time for cutting the grid first and denote it by TG. So assuming that the scanning by the laser or if the case may be by the knife is occurring at a constant scanning speed, then the time taken will simply be proportional to the distance that is to be covered. Let us try to find out what that distance is. So, uh, so this problem is symmetric in the x and y directions. So let us work for one direction first, and maybe we can simply multiply that by two times to obtain for the other direction as well. So when cutting in the x direction, we see that this entire length of A has to be cut once, twice, thrice, and four times. So I can write 4A, as well as there are some other portions which have to be cut, which correspond to the grid lines in the x direction. So this 1, 2, 3, 4, and 5. Similarly, on the other side, 6, 7, 8, 9, and 10. Now, each of these cuts is actually corresponding to a length of 2A, because here the region is already pixelated and squares which have a side of length A each, and I am making 10 cuts or 10 scans of length 2A. So these are all of the scans in the x direction, and since the problem is symmetric, I can simply multiply by 2 to obtain the scans in the y direction. And we have further have some relationship between the capital A and small a, as we can see that. So 1, 2, 3, 4, 5, 6, 7, 8. So capital A is actually equal to 8 times small a. Thus, we can have some constant of proportionality k into 2 times 4a plus 10 times 2a, so 28. So this is 2k times 4 into now capital A is equal to 8a plus 20. So this is 2k times 52a or 104a times some proportionality constant. Similarly, let us find the time taken for scanning the contour. Mm, Maybe we can. Is there a variable given? Okay. So maybe the time taken for scanning the contour can be denoted by TC. And again, if we assume that scanning speed is constant, the time will simply be equal to some constant, the proportionality constant times the distance, which in this case is 2d in the horizontal direction and 2d along the y-axis. So 4k times 4d. And again, I further have a relation between this smallest length scale A and D, which is equal to D is equal to 4 times A. So this time is equal to K times 4 into 4A or K times 16A. I can actually find the ratio of these two quantities. So T grid by T contour equal to K times 104A by K times 16A. So both K and A get eliminated. And if I divide by 4, so 26 by 4 or 13 by 2. So this is 6.5. Therefore, the time taken for grid cutting in this layer is almost equal to 6.5 times the time taken for cutting the contour. This gives us some idea of the scale of times which is involved in these processes. The seventh question asks, what are the advantages of Kira's paper lamination technology when compared with cubic technologies LOM? So, does it give higher strength? Yes, we saw that the strength was 25% higher than even the equivalent wood. There is no distortion or curling. Yes, this is because the of the use of the hot plate. which actually and because after the hot plate is removed, the material is allowed to expand freely, and this leads to the relieving of stresses. Because the residual stresses are at a minimum, there is no distortion or curling during further processing. And yes, in the minimal internal strains are also present. And fire hazard is not there because even though we are using a hot plate, we are not using a laser. For cutting, we are only using the mechanical knife. So actually, the danger of a fire hazard or a similar other health hazard is greatly reduced. So in fact, all four of these are the advantages of Kira's paper lamination technology over cubic technologies laminated object manufacturing. And question 8 is asking us as to what is the primary disadvantage of sheet additive manufacturing processes compared to other AM processes. The lack of adaptive slicing. Yes, this is one aspect we have constantly been covering. That even though there may exist one or two processes which can actually use this adaptive layer thickness, for most of the processes or for the typical sheet-based AM process, the slicing height is fixed in each layer, and thus adaptive slicing cannot really be exploited. So this is definitely a disadvantage. The lack of materials library that can be processed. So over the course of these lectures, we came across multiple processes. Some of them are even capable of processing plastics, ceramics, definitely metals, and even among metals, even those metals which are metallurgically incompatible with each other, or which under normal course mixing them would lead to poor diffusion, poor bonding, or would produce some precipitation of intermetallic particles or the formation of deleterious second phases. Even such phases can definitely be combined using some of the other suitable sheet additive manufacturing process. So this is not a disadvantage because it has a very vast material library which can be processed. Higher energy requirement, definitely not. And specifically in the case of ultrasonic consolidation, we see that the energy requirement is even as low as 5% of some of the other processes such as DED or some other conventional welding processes. And regarding the health and safety hazard, we saw that in most cases the sheet additive manufacturing processes are suitable even for office environments. There is no hazard such as related to powder or the use of lasers, high power lasers, or any toxic fumes, or even the need for a protected inert environment. So the primary disadvantage is simply the lack of an adaptive slicing. And with that, we have come to the end of the questions for this week. So if you have any doubts, now is the time to ask. So if not, thank you for tuning in. I am Sourav Goswami from IIT Bombay, and I look forward to seeing you next week. Thank you.
Thank you, sir.
Thank you, Indranil.